So this is a general outline for how the presentation should flow. I wanted to start off by going through some brief introductions for who we are at Intech and what we can do for you. So here's our staff that you could be directly interfacing with to get your projects quoted or designed. First off, we have Tim Combs, our president. He's been in and around the industry for over 25 years, and he's a very knowledgeable resource of industry history. The second set of people highlighted here are our sales team. They consist of 6 primary individuals, and they'll be the ones interfacing, getting quotes together, and helping manage our sales. The top 5 individuals are Bill, Luke, Jack, Joe, and Corey. They're our sales managers in their respective markets for our product offerings. Then on the bottom row, we have Jim Sorrell, who is our global sales manager for Hydroway. He's been here a long time and is extremely knowledgeable of the product line. These are the people that can interface with you to get you the right products for your project. For our operations staff, Josh and Jim are our head of operations. They manage our warehouse staff who works to make sure the products are bundled, handled, and shipped to you in a neat and timely manner. They are very detail-oriented people, and they take great pride in representing our company. And last but certainly not least, we have our engineering staff. Our engineering staff is currently comprised of Sam Pappas and myself, Sean Hibbets. We take care of engineering quoting, design assistance during the design phase, which includes calculations, drawings, and VE options, and can also help out during installation. We look to be innovative to try and come up with unique, cost-effective solutions when presented with tough design scenarios, so please feel free to reach out to us if you need assistance with seeing one of our elements can work for your project. We also spend a lot of time helping train consultants and specialty contractors to make sure everyone is on the same page. An additional benefit of reaching out to us is we retain the services of a good number of very experienced geostructural engineers throughout our territory, and they assist us with completed turnkey engineering submittal packages for our designs. So we can definitely do our part in providing high-level engineering assistance in many engineering situations. So we currently have 2 warehouse locations, Caseyville, Illinois, which is pretty much St. Louis, and Livonia, Michigan, which is pretty much Detroit. We represent these brands on the screen as well as some others that help us provide a wide array of engineering solutions to our partners. The first brand is Chance Atlas, which represents our line of helical anchors and resistance piers, or push piers. We are one of a handful of Chance distributors representing a good portion of the middle of the country up through the Northeast. Chance is an extremely well-respected manufacturer, having over 100 years in the industry, and also having very experienced engineers that can give additional recommendations or gut checks for special scenarios. The second brand is MagnaCore, which is our brand of hollow bar micropile. We will discuss how that works today. This is a competitive option compared with a cased conventional micropile. Ours is a great one-pass method of installation that's very effective in maintaining an open hole in collapsible soils without having to advance or withdraw casing to keep the hole open. Then we have Carbon Bond, which is our carbon fiber structural crack repair system. It's a composite resin carbon fiber reinforcing that provides tensile strength to existing structures and can help increase the capacity of the structure or help repair it if it's undergone cracking failures. And then finally, we have Hydroway, which is our geosynthetic wrap strip drain product. It's an effective way of transmitting water through an underground pipe channel without concern of moving soils with water flow. It has a very high permeability and flow-through rate that is a cost-effective underground piping and water management solution. So I wanted to include my contact information, and if you have any questions or comments on anything you see today, anything you'd like to see presented in the future, or need design assistance, please feel free to reach out and contact me at any point. So here is a graphic representation of our footprint with Chance helical piers and Atlas resistance piers. This is our territory where our partners are based. We have a lot of activity and experience in these areas with local engineers and contractors. This image shows the footprint of where we market our hollow bar micropile MagnaCore. As you can see, we're not restricted to a territory to offer this solution, so please feel free to reach out to us if you need assistance anywhere here. Additionally, we have no territory we're restricted to for Hydroway. We currently sell and market this solution worldwide, so please reach out to us if you have a need for this product. So now I'm going to go through the components and installation. So this slide will serve more of a purpose as a handout later on. The main thing to take away from this slide is that hollow bar elements are just a special type of micropile. All it is a small diameter grout column with steel reinforcing. They can be used in new construction, vertical or horizontal applications, and even for retrofit, just like conventional micropiles. They act as a deep foundation element that takes the loads from a shallow foundation level through something weak or sensitive to a material that is dense or hard. Hollow bar micropiles are a very effective alternative when comparing to conventional micropiles that has to be cased during installation. I'll discuss this in a few slides. So as I said on the previous slide, the applications for a hollow bar fall into these major categories: new construction, underpinning with settlement and stabilization, earth retention, and slope stabilization and tunneling. We typically see hollow bars specified by engineers when the soils will collapse in an open hole drilling scenario, or when you need to get some extra capacity per foot based on the moderately pressurized installation for hollow bar, which I'll discuss. So like I said before, MagnaCore is our brand of hollow bar micropile. Our materials are a non-domestic form of hollow bar that we offer to the market at a great price. Our engineering staff interacts with specialty contractors ranging from small to extremely large companies. We look to be an additional hand to help in capturing and growing our partners' markets. We can help you work through coming up with an efficient design with our in-house engineering staff. Some additional bullet points that can lead to hollow bar being the more advantageous system is for difficult soil conditions. As I discussed previously, one of the big advantages of hollow bar over conventional micropiles is its ability to maintain a hole without having to advance casing due to the constant pumping of grout. So the grout can be designed to have a high enough fluid density to add weight to the hole and coat the walls to keep it from collapsing. Another benefit of hollow bar anchors is that the drills for installation that we'll talk about in a little bit have the ability to have a hammering action applied to the bar, kind of like an impact drill. This helps penetrate through tough rock and boulders, and with this system you can also develop rock sockets over relatively long lengths. Third, the one-pass installation method can allow for much less labor to be required during element installation. After drilling, the steel components used as the drill string are disconnected from the drill and left in the hole, and then that's all terminated with a nut to act as the pile's reinforcing cap. Additionally, our elements are advantageous for limited access. We even have a man-portable equipment on a dolly system, and we can cut the sticks of bar down to shorter lengths to allow for tighter access. Finally, the elements are installed with low vibration and corrosion protection are additional product benefits. We have a number of different add-ons that can also provide additional corrosion resistance than bare bar, and there's also a flow coat on the bars that helps alleviate some corrosion concerns. So one of the big takeaways for this system is that the cost comparison shouldn't just be made at the material level. The cost of the entire system installed should be compared. A conventional micropile, when it requires a cased installation due to collapsible soils, might have a low material cost, but it has a very high labor cost. Compare this with the hollow bar option, the cost of the materials may be a little bit higher than the conventional thread bar, but the labor savings typically makes up for the material cost.
Alright, now I'm going to go through a quick video of the installation of a hollow bar micropile. So this is the general layout of equipment required for installation. This includes a hydraulic power pack on the left, the drill with an MYM rig, and a grout plan on the right. This MYM rig is a special piece of equipment, and you can usually just have an excavator or skid steer for the installation. The first step is to lay out all the pieces for one element next to the element location. This is a good way to ensure that you have a good understanding of how far you've progressed on an element within a hole. You know how many bars of steel you have gone into the ground if you only have a few left. For instance, if you start with 5 sections of bar and you have 3 in the ground, you can obviously see that there's 2 left. So before you start installing, it's necessary to mix up some grout. We typically look to add one 94-pound bag of cement for every 5 gallons of water. This will result in a 5,000 psi mix within about 7 days of grouting. If you're planning to use a flushing grout or use a higher or lower strength structural grout, this mix should be adjusted. It's important to thoroughly mix the grout to ensure the cement particles become fully hydrated. On this model of grout plant, we accomplish this by using a colloidal mixer. Once the cement particles are thoroughly mixed, you can transfer the grout from the mixing tank on the left to the agitating tank on the right. This can be held for an extended period of time and keeps everything mixed and suspended. A big key in fitting the components for the elements together is to use some sort of lubricating grease. We typically use copper coat, thoroughly applying to any threaded portions of the element. Now, put the first coupler onto the end of the striker bar of the drill. Apply copper coat to the end of your bar. Now add the bit to the end of your bar. These parts will make up the lead section for the element. Now you can raise the drill to allow room for your lead section. Then add your lead section onto the coupler that you already attached to the drill in the previous step. Before you start advancing the pile, the drilling operator should tell the grout plant operator to start pumping grout. The drilling operator should look and verify that there's grout flowing out of the end of the bit, and then he can start advancing the pile. The operator will advance the drill with rotation into the ground, making sure that grout is flowing out of the hole the entire time. The piles advance with torque and downward force applied by the drill and mast. Additionally, if necessary, the drilling operator can use the hammering action of the drill to hammer through any dense or stiff profiles. Once the first bar is nearly all the way into the hole, you should plunge the hole 3 to 5 times before adding the next section of bar. This helps flush the hole, erode some of the hole away to create a ribbed profile, and create more engagement with the soil. Now disconnect the steel from the drill using the clamps, if available, to break the threads. Additionally, spinning the drill in reverse can help break the bar loose. Apply copper coat to your next section of bar, then add your next coupler. Take this extension and thread the coupler onto the drill. Now you can lower the male end of the extension into place and rotate the bar into the coupler to have it thread itself onto the bar in the hole. With everything reattached before advancing the pile, the driller should tell the grout plant operator to begin pumping grout. Make sure you control the flow of grout out of the hole to minimize waste. Too much flow can result in unnecessary loss of grout and an inefficient installation. Repeat this process, adding extensions and plunging the hole until you achieve your design depth. Once this depth has been achieved, the hole should be plunged 8 to 10 times to really get good engagement. At this point, with the bar sticking up out of the hole, you add a hex nut, a bearing plate, and another hex nut to terminate the pile. This entire assembly will then get cast into the footing. And those are the general steps for a hollow bar micropile installation.
So here's a breakdown of the components of a hollow bar element that has been completed. The first few breakouts are the termination, final injection grout, coupler, and bit. We will go over these in more detail in a few slides. The second set of components to look at are the soil cement grout body, the steel bar itself, and the centralizers. So a little more about the bar. The bar is a continuously threaded steel tube. The threads are typically left-handed threaded. The bar is usually shipped in 3-meter sections, but this can be cut into smaller sections for low headroom type installation. The bar is specially manufactured to meet the specifications for ASTM A615. MagnaCore is regularly tested for the cross-sectional area, thickness, tensile strength, and yield strength. We also contract out third-party testing to make sure that what you get on site is good or better than what you ordered. So with the bar, there are typically 2 types of hollow bar, namely T-thread and R-thread. R-thread stands for rope thread, and T-thread stands for trapezoidal thread. These designations describe the outer profile of the thread. So this is how the naming convention breaks down. For example, for the name R32S, it has 3 parts. The first part is the letter designation of the bar, so rope or trapezoidal thread. It will have either a T or an R here. The second part of the name will be the outside diameter of the bar in millimeters, so in this case it is 32 millimeter outside diameter. The third part is the hole modifier, which refers to the hole size. These are not always consistent between manufacturers. At the end of the day, it is most important to consider the specific engineering properties of the bars from specific supplier you're getting them from. We generally have the strongest bars in each line in the market, so make sure you consider a smaller bar size compared to our competitors. So for instance, it's not uncommon that our R38 bar can outperform T40 bars from other suppliers. So the next component I'm going to talk about is the couplers. These are internally threaded sections of tube that connect consecutive sections of bar. There are also gaskets inside that engage with the end of the bar to seal the internal hollow section. This is to keep grout fluids from going between the threads and squirting onto the installation crew during pile advancement. The coupler sections are designed and tested to verify that they are higher strength than the bar itself. So the third component we'll go over is the bits. The bits are heavy steel components that get threaded onto the end of the bar. There are multiple styles of bits that can be selected based on the anticipated soil conditions, or rock socket if necessary. The first one at the top is a button bit. This bit is good for pulverizing bedrock for rock sockets of substantial length. The second style that we typically carry is the crosscut bit. This is advantageous for dense or stiff profiles and even some moderate rock socket lengths. And the last style we typically carry is the clay bit, which is good for clays and softer soils that don't have gravels or sands. There are other types of options of bits that we can obtain, so if there's a specific style you are familiar with that you would prefer, please feel free to let us know. These bits come in different sizes, anywhere from 76 millimeters all the way up to 250 millimeters. But there are typical guidelines for how big of a bit to use for a size bar, so just reach out to us if you have any questions about that. So it's important to understand that each of the styles of bit have ports that allow for the grout to flow through it. This is important and an important key to installation, that you always have to be flowing fluid throughout the bit during pile advancement, otherwise the bit can clog or plug up. Always remember to flow before you go. So finally, the termination assembly consists of a few pieces and is the last component we're going to discuss. The termination assembly consists of a bearing plate with a hole and a few hex nuts. Once the design length has been achieved for the pile, the nuts and plates are assembled and any excess bar is cut off. The assembly typically is then cast into a footing. So a piece of equipment that's necessary for system installation is a grout plant. This system takes cement particles and water, combines them very intensely using a colloidal mixer, and pumps the grout through the system all the way down to the bit. An important key is to make sure that you always have enough cement to finish an element. You don't want to be going to the store for extra cement with wet grout in the tanks. We typically look to achieve a 5,000 psi mixture for our elements, and that is generally a 94-pound bag of Portland cement mixed with 5 gallons of potable water. This first slide demonstrates how the pieces go together for an excavator-mounted installation setup. It's important to note that the drills run off of hydraulics, so it can be run off of the excavator if the excavator has sufficient pressure and flow to meet the needs of the drill. Otherwise, an external power pack can be used as a supplement to smaller equipment or equipment that doesn't have hydraulic capabilities. The second setup is for a skid steer mounted setup. Similar to before, these can run off smaller pieces of equipment, but if you need extra pressure and flow, a hydraulic power pack can also be used. And finally, we also have man-portable drill systems that can be moved by hand. There are some limits to the bar this one can install, and the specific drill specs and soils should be checked. So the following slides will demonstrate the general steps for element installation. The first step is you install the lead section, and the lead section consists of a bit, the first section of bar, and a coupler to attach to the drill. And for clarity, I have omitted the drill above. So the first step to advancing is to start pumping grout. And while you're pumping grout, you apply crowd and torque. One important note is it's also possible to use a thinner grout than the design mix. We call this the flushing grout. It can go as thin as water, but less cement results in less fluid density that can also cause hole collapse. We will have to displace this grout at the end of element installation as well. So when you're drilling, someone should always be looking to verify that grout is flowing out of the hole. If there's no grout return, it's important to assess the reasons. Additionally, if grout is flowing too quickly out of the hole, the flow should be reduced as to reduce the amount of waste. Therefore, the drillers and the grout crew should be in constant communication with each other, even if you have to do it with walkie-talkies. Another thing to note, the hole created by the system is taken to be the diameter of the bit. However, since we're pumping under a slight amount of pressure, the grout flows into the void space of the soils. It also wears away the sidewalls of the soils. This is especially advantageous in sands and results in much higher engagement with the soil. After each section of bar is advanced nearly all the way into the ground, it is good practice to plunge the hole 3 to 5 times. We've been on projects where the contractors didn't do this, and it resulted in poor pile performance. So after you're done plunging, you can disconnect the coupler and add the next bar section. You can then advance the system, making sure to pump grout before advancing the steel. Another feature of hollow bar drills is that they're able to apply a hammering action. This hammering action can help penetrate dense, cobbly, gravelly soils and penetrate into bedrock. You can see the vibration helps advance the pile through this dense layer. And with every extension, don't forget to plunge the hole 5 times. So now you just repeat this process of adding bar until your design depth is achieved. At this point, we'll say that we've achieved our design depth. The hole that has been created is full of the thinner flushing grout, so it's necessary to displace this material with structural grout. If the hole is drilled with structural grout, this step won't be necessary. So you can see here the structural grout has filled the cavity of the hole. You should see the structural grout coming out of the top of the hole before you consider it completed. At this point, it's important to plunge the hole 8 to 10 times. Doing this creates much more engagement at the bottom of the hole. Now we add the termination components per the design. The designer of the pile cap will designate the elevations the plate should be at. The plate and nut system allow for ease of adjustability of the plate. Finally, the termination gets cast into the pile cap. So an additional application would be something battered, like tiebacks. The specifics of installation are pretty much the same, just at an angle. They're typically 10 to 20 degrees battered and are used for providing active support to a segmented wall that can't support itself. The elements engage with a whaler that transmits the loads from the elements to the piles or wall segment sections to help add rigidity to the wall. The biggest thing to understand for the installation of these is that they are top-down installation. First, piles are driven into the ground. Then excavations are made in lifts. The soils are excavated along the length of the wall, down to the first level of intended installation of elements. At this point, the element is installed and engaged with the wall. So for tiebacks, the general form of post-tensioning involves pulling on the bar to elongate it, and while it is still elongated, you thread the nut down onto the bearing plate and whaler. We accomplish this with some special components that hold the load while still giving room to thread the nut onto the bearing plate. This process is repeated along the plan view length of the wall at all the elements to be installed. After the row of elements are installed, the remaining soil is excavated, or the soils are excavated to the next row of anchors. Soil nails, which are a passive system, are also installed this top-down method. However, it's a passive system, so there typically aren't components to react against. So now I'll turn it over to John Patterson with Word Drills. He'll give a bit of a company introduction and some insight into drills and drilling.
Thank you all for being here. I'm John Patterson with Word Rock Drills. So Word Rock Drills, we began 15 years ago. We're in our 16th year. My history is I helped found TEI Rock Drills with my father 40 years ago. And so we got into all this, and 15 years ago, we decided to have to go our separate ways, and I feel it's a very amicable situation. We are in the same field, but we can talk to each other, and praise the Lord for that. And what we're after at Word Rock Drills is World of Rock Drills, and the other reason is I'm a Gideon, I'm a Christian, and the Word of God. It came from that. John 1:1, in the beginning was the Word was with God, and the Word was God. And Word, I kept thinking, World of Rock Drills, it fit the name of the company. Our mission is to be a great company that enhances our family's quality of life for many generations through our team, customers, and those around us. This is a field where we meet people over and over again. So the best business situation is where everybody wins. And if it's anything I've learned in all this time is if everybody wins, business keeps going. So for Word, we're always looking for how the customer will win and making sure we win at the same time so we can keep going. But we want the customer to win. That's the goal. So through that, Reed and I are the salesmen at Word. We'll be adding another salesman this year. And Spare parts are probably what everybody's going to ask about. And I've started two businesses as a pirate part manufacturer. And the reason I got into business is because the OEMs ran out of parts. We have parts in stock. And people like that you can call in and talk directly to Reed or myself or Clayton and get answers. So if there's a problem going on with the drill, you can call in and talk directly to a person right now to get it solved and to get the correct parts out that day. Construction's construction. So every day you run into something different, and the name of the game is options, and options are power, and that's what we're about. For the drilling attachments, we set up mounted on excavators as small as 2 ton onto the boom. We do have aluminum feeds for those lightweight needs. We have drifters from 1-inch holes up to drifter-wise, I would say 8-inch holes. And then we also have rotary drills, which will go to 18-inch holes. You can operate wireless or with a tether. So most folks are operating from in the cab so that they can get the positioning where they want it through that radio control. But if you want to be drilling right out on the end there, you can operate it right at the source where you're drilling the hole also. So the controls are a simple belly pack that weighs, I think, 2.5 pounds. So it's not hard on the man to carry it all day long. One of the nice features of the radio control is once you hit your sweet spot, you can press auto drill and it'll just keep drilling where it's at. So once you find where that position is, hit that auto drill. If you need to click out of it, you just click out and then manage it, and then you can click it back on. It's a button. It's on and off at the location. Your rotation and feed also have pressure controls on the radio, so you can increase your pressure on either one or decrease at a moment's notice when you need it. You're going to have the driller who's in the cab, the rod handler, the helper who's out on the end loading the rods, and then the grout man. If you know you're going to run into multiple angles, having the 2 rotators there, which are item 1 and item 2 there, those 2 rotators, one on the top and one for your lateral, that gives you, with the movement of the bucket, every imaginable angle that you could conceive getting. So those 2 options are the way. The first one for the lateral movement is automatic. That comes with the unit. But the second one on top is an option because there's many quarry people who don't need that second option. What that also allows you to is to drill on either side of the boom, because it'll just move its way all the way around the boom. So the second one's a good option if you know you're going to run into multiple angles. In the front, you can have a clamp, a simple clamp, or a clamp breaker, and or just a regular manual centralizer. If you start with the clamp breaker, it's great for grabbing the coupling on soil nailing, but it also gives you options for casing in the future with a rotary head. So now you've got both options covered. Comes with a industry almost standard energy chain for handling the hoses, which works quite well. The feed itself, we can make 2-speed also. So it can give you either fast speed or the second speed with a lot of grunt. And the feed itself, we haven't run into people bending it. It's a piece of strong structural tube with 3/4 plates on each side, and it's very strong. And the other thing that I really like about ours is we have double 80 chain. Double 80 chain ain't going anywhere. It's strong. It never fails, and that's the reason we went with that from the beginning. I wanted to have that on it, so we're trying to design problems out of it. So if we can make it strong enough where we don't have problems, that's our goal. So our first option today for soil nailing is the EX540, and it's set up primarily for the 30 and 40 millimeter drill rods. and 4-inch holes, 4.5. Has good high torque for installations, and it's set up well for those smaller diameters to give you some high production in the field. The EX560 then, which you see next, is for 45 millimeter rods, and it will drill the 52 millimeter rods also, and we're looking at 5.5 and even 6-inch holes with it. And both of these units have the integrated grout swivel, so there's no exterior grout swivel associated with it, as you can see from the drill there. The grout goes right through that front swivel. It's protected, so the grout does not go back up into the drill, sealed off against that with an actual physical space to not permit it to go back through, and makes it for a nice compact package and very good for threading and unthreading. Use a clamp on the front to grab the coupling, unthread, put the next one on, go back to work. You're always guaranteed to unthread at the right location. The 560 unit for the larger holes, you're going to want a 20-ton excavator. 15-ton can even work if they can combine the pumps, because you'll want 58 gallon a minute to be highly effective. Then we go into the Euro drill, and that will get you up to the 76 millimeter rods, and it will go down also to the 30 millimeter. The Euro drill is a very known product, very accepted in the field, and this one in particular, the RH10X, will permit you to have a percussion drill, and you can even switch it out to a rotary drill, a high torque rotary drill up to 10,000 foot-pounds. So it's a very versatile unit like that. It's not going to happen quickly in the field, but it can be converted to both options. It does require an external grout swivel, but it will get you into those larger diameter soil nails. The versatility here, you can see from the mounting plates that there's 2 pins that mount the unit to the drill. So we have all the percussion drills, plus we have the rotary drills with a through swivel, so you can't even soil nail with them in softer materials. But it's just very versatile. Some of the rotary heads there are also set up for installing screws. For if you have to get into a small area, you can even switch the feet out and put it on a 5 and even 8-ton unit with the pneumatic drill on the far right. With a 375 compressor, it's a pneumatic percussion drill with hydraulic rotation. And we've had clients who have used up to even 52 millimeter rods with those. It does require an external swivel also, but the big thing is for if you have tight access, it can be accomplished even with the bigger rods with that pneumatic drill. And all of those 2 pins and the hydraulic connections, which come standard from us to switch quickly between the units, that versatility is what Word is selling, what Intech is representing. So you have options. And in today's construction world, options are power. Maintenance, apply grease to the grease points. The charger, charge the battery. Every unit comes with a spare battery, and just keep that spare battery charged. It's typically an 8-hour work process with each battery. Keep around additional wear pads and spacers, which are very simple and inexpensive items to have around. If you are using an oiler, check your oiler twice a day at lunch and afterwards. And check your feed chain. If the feed quits working, it's just getting a little slack, and just have to tighten that up. It's a very simple field fix. Most of the time we use a greased front end for the rotation. It's optional. You've got your grease zerks are there. If you want to use a lubrication on the front side, you can. But with grease makes everyone pay attention, and it's pretty foolproof outside of the people applying the grease. So a high temperature grease in that front end has proved to be very, very successful. So job site and project details. The thing we'll need to know is like what type of material we'll be drilling into. And so whether we use the rotary or the percussion drill, what size bit and bar are going to be used for, what kind of pullback strength you need. So we set up appropriately for that. Your accessibility, the mounting between different excavators is a simple 6-bolt mount onto the unit. And so you can switch between excavators by changing that mount out. And also what kind of production you want to have. And so many times you can live with you're waiting for the next guy to go, so the production doesn't have to be high production. But if you need the high production for a big soil nail wall, we'll set up accordingly for that. It's getting to be more of a known thing. Typically, people will pressure grout at 1,000 psi, and they'll go in with the thinner, more neat cement to start the hole. And the big thing is to keep the flushings coming out of the hole while you're drilling down. If they're not coming out, then we've either plugged the bit or we've hit a void. And so keeping those cuttings coming out. And then when you reach the depth that you're to, thicken up that grout and set your rod at that point in time. The big thing I've seen on the job sites is your communication between your driller and your grout man is of utmost importance. Hopefully they like each other. Hopefully they get along well. That's probably the biggest variable in everything. So you want them knowing each other and having a history of working together, and be patient with it. I think most people want to keep their jobs and they'll figure out how to do that, but that's something to be very aware of going into. If they inherently don't like each other, you might find them a different job and get someone else in there. The crosscut bits are used a lot of times for really hard rock in mining, and sometimes that's the case here. And if it's hard rock, get the bits for that little extra money that have the carbide tips on the end. Because we've run into many jobs where they use the steel bits and it's in hard rock and it's dull right away and you're just beating the drill up at that point in time. It's worth that extra $30 or whatever it is to get the carbides on the end of the bit for sure.
All right, thanks, John. Now I'll get into the major design principles of hollow bar elements. It's important to note that the things discussed in this presentation are for informational purposes only, and this presentation shouldn't be used to design an element. There's a lot of great information out there, and these are some references we typically use to validate our designs. So with geostructural solutions, there's a few things to consider. First, I'll go through the major principles for the geotechnical capacity. And the geotechnical capacity is comprised of two things, the skin friction and end bearing. The side friction is generally taken to be along the surface area of the sides of the grout column diameter. So we would take this area, which is a function of the diameter of the bit, and multiply that by the bond strength. There's also a factor of safety applied to this bond strength, so it can be compared to a design load. This area times a strength results in a resisting capacity. So with geotechnical systems, there are typically a few layers of soil and/or rock. Each of these layers has a section of cylinder that passes through them. It is intuitive that the density or stiffness of various soils results in varying amounts of resistance friction. For example, a soft clay probably wouldn't resist a load as much as an intact limestone. So with that friction resistance equation before, and knowing how much of each cylinder passes through each zone, we can calculate how much skin friction capacity can be counted on for each layer. An important note, there's typically a length we disregard at the top of the elements for undocumented fills, active zones for wet and dry conditions, and other cases of soils that shouldn't be counted on for resistance. The design methodologies typically have a more in-depth description of what to use for unbonded lengths, so use those. And a similar thing needs to be accounted for in tiebacks and soil nails. The soil from the wall to a point of potential failure should be disregarded for the soil resistance calculations. Because if this section of the soil failed, that material can no longer support the pile. So the check we do on the system is to determine if the capacities of each layer are greater than the applied load. If there is more capacity than load, the system is okay. If there is not enough resistance, the length of the pile or the pile diameter should be increased, or even the number of piers can be increased to decrease the total amount of load on each element in a system. So another component of capacity that can be used is end-bearing capacity. However, as these elements are relatively narrow in the context of geotechnical engineering, this is typically disregarded unless it's in bedrock and the bedrock is quality rock that has been cored and tested. There are additional criteria that are typically outlined in the design methodologies. So the table on this slide gives values of what we typically use for ultimate grout-to-ground bond for soils. You can match up the types of soils in each layer with this table to determine how much ultimate strength you should use for your bond values. So the column for type A is a conventional gravity grout system, whereas for the hollow bar system, you should use column E. So you can see the values for column E typically have higher values of bond strength based on it being installed with a pressurized grout. This is especially notable with sand layers. So as you can see here on the left are some elements that were installed as solid bar. These elements are smooth-sided. Then the next three on the right are hollow bar elements. Based on the pressurized grouting and plunging, it created a very ribbed profile of grout, which allows for more surface area to be in contact with the soils. In this manner, our elements typically overperform than what we initially designed. Alright, so the second check is the structural capacity. So these sets of equations represent the structural checks we do for an applied load. These checks are for compression and tension. As you can see, for a compression load, the capacity is shared by both the grout and the steel. I'll get into this in a little bit. For tension, the only term that is used for supporting the loads is steel. So the steel is the limiting component for structural support for these elements in tension. And this is because the concrete doesn't do very well in tension. Additionally, if any microcracks were to form, the grout would become disengaged, and at that point, the only thing transferring the loads is the steel. You can see the steel controls in this case. If this were in compression, those columns would still be able to transfer the load, so the grout could still carry some of the stresses applied. So these equations are relatively simple, but have a few nuances. The safety factors are different from one another, and there are different factors of safety based on the methodology you are choosing to use for design, so make sure you are paying attention to that. Another key principle is related to strain compatibility. So we could use a really high yield strength bar, however the grout would likely fail at the strain required to fully engage the steel yield strength. Typically we limit this yield strength of the bar to 0.003 times the elastic modulus of the steel. And finally, the only way to really check these elements is with a load test. Typically, as long as end bearing is disregarded in the element design, it's possible to test these elements in either compression or tension. But this is up to the discretion of those involved for the project.
Alright, now I'm going to run through a few things for load tests to verify the capacity of the elements. As a disclaimer, it's important to never allow anyone to stand behind or next to an element that's being tested. If anything were to fail or release under pressure, it could be very dangerous and lead to injury. So these are the general steps for a load test, but please reference the specific test methodology reference such as ASTM for specifics. The first step is to install the element. Once the element is installed, you set up the load test equipment and hook everything together. Then, you apply an alignment load or seating load, which is typically 5 to 10% of the design load. This takes the slack out of the connections that could cause erroneous deflection. Deflections after the alignment load step are considered to be a combination of steel and soil strain. After the alignment load step, advance the load test by applying consecutive loads and holding per the load test schedule. Some load test styles require unloading between each load step advanced, whereas others allow for progression to each consecutive load without unloading. I'll talk about this in a minute. So the load steps are increased until the maximum test load and held for creep. This maximum test load is usually 2 times the design load. After this step, the load steps are progressively lighter loads until the pile is fully unloaded and all of the decrements required by the test have been performed. The results are compiled, plotted, and compared with the model to determine if the piles are adequate for support. So this slide shows the 2 styles of load tests that can be performed. the cyclic test and the incremental test. The cyclic load test is performed in a manner where, between each consecutive step, you unload the pile and record that unloaded deflection. This is taken to be the deflection of soil or residual movement. This test takes a bit longer than the incremental test style shown on the right. The incremental load test is performed by advancing to the next load step without unloading the pile. This results in an overall picture of the pile with respect to the ultimate load, but you lose the resolution of the effects of each load step on the soils. This style is typically a bit faster to perform as well. So for micropile tiebacks, there is a few types of load tests that are recommended to be performed on the piles. The first type is the performance test, which helps to verify the pile capacity, load deformation behavior, etc., and gives the opportunity to refine the pile design to be more efficient. The second test type, which is typically performed on the rest of the tiebacks for a project, is an incremental style load test, which is quicker confirmation of the pile performance compared to a performance test. If the results are much different than the performance test, it is typically advisable to perform a performance test on the next consecutive tieback. And finally, a creep test step is performed at the maximum test load for each type of test. If the pile results fail this initial creep criteria, an extended creep test, which is a longer hold, is advised. Additionally, it may be recommended to plan to perform an extended creep test from the get-go if the soils are known to have high strain or low strength characteristics. So this slide is a blown-up version of the cyclic load test for more clarity. You can see that on the graph, the lines go out to each individual load step and come back to the alignment load axis. There are a few individual touch points along this axis that are the individual residual movements of the soil from each load step. So, load step 3 has its own point where it rebounded to the axis, and this is the deflection attributed to the load at step 3. The overall residual movement, shown on the left in red, is the added up set of deflections caused by each load step. The rest of the movement is attributed to the elastic movement of the piles, which should be recovered. The reason we perform a load test on these elements is there isn't really a good or empirical way of attributing the effort required for installation to a capacity. So we can develop a model for the soils and maybe have a good idea of how we think the soils will respond, but we need to do a load test to verify our model. We need to test if the element at that specific site can withstand the loads being asked of it. And if it performs well, we can accept it. And if it's not as good as we think it should be, we can see that, assess it, and pivot to a solution that will work out best for everyone.